Okay, next up is this idea of using lattice models. These are special cases of decision analysis trees that I talked about the last time, and they're going to allow us to introduce another uncertainty variable into our models in a manageable way. So. Um, Last time we talked about decision analysis, I explained what the var curves were, right? Cumulative distributions of net present value using, one source of uncertainty. We could introduce other sources of uncertainty, but wouldn't be able to track which one was having the effect. Um, but that's one approach. Another approach could be, using them in combination with a decision tree. So using this decision tree, for example, we could have a distribution of each of these expected values, and calculate the resulting values for each choice. And that's fine. It's great. This is great to allow us to depict the big picture. But if the decisions are made each year instead of just a couple of, see, these are just have a couple of decision points. We have to make a decision each year like we might in putting together a plan for implementation of a large project. Then there's a problem. You're really limited only to 2 or 3 periods just to get a big picture. So if we had, let's say, 3 choices each year, there's the first year, here's the second year, and these have all these. So if we had 10 years, 3 choices each year, that leads to 59,000 plus alternative paths. So that's just too many, right? Too many. So it's really not workable. So if we were to introduce, let's say, demand we already have, if we wanted to introduce another uncertainty using unit revenue, only 2 choices, not 3, just 2, and we wanted to go for 15 years, and we wanted to look at maybe these 3 options, we'd have to do something 3 times. And this would be the same. I think I've already explained this. This is the planned stage construction that I had I'm going to show you in the lattice model video later on. So I have these keep having these stupid things fly in. Hold on now. So the problem is, so if we have 15 years, 2 uncertainties, 15 years, that means more than 30,000 alternative paths that we would need to look at. It's just not workable. It's really not workable. And so we use this idea of a binomial lattice, which makes some simplifying assumptions and allows us to make this decision tree more manageable. Okay. So we're able to look at more details by making just a couple of assumptions. So, for example, every year things will change kind of in the same way, up or down. Or let's say have the same magnitude of change. And each state leads only to 2 others. So in the next year, something will either go up or go down. The value will go up or go down. And the later states are related to the earlier states. So if something goes up, it's a percentage of the previous year. Right? So this state here, let's say the value here will either go up by some factor or down by some factor. That's the assumption. So if I were to expand this out a bit, you'll see the advantage of this approach. So if I do the first year, it either goes up or down. Now if it goes up again, then I have that factor u multiplied twice. If this one goes down, then it's a factor up and a factor down times the original value. Well, if this one goes up, that's the same. So I've just clipped off a whole branch of a huge tree of those 30,000 plus alternatives. I've just clipped off a whole bunch of them. Similarly here, I can keep going here. You see, I just clipped off another whole set of branches, and so on. So the values are non-negative. If you're talking about profits, you got to be careful. This is used for evaluating stock market decisions and other kinds of financial decisions. Right? Paths are independent, really easy to construct in a spreadsheet. I'm going to go over that in the later videos. I've done an example. So let's say I want to explore, just a little example here, I want to explore all options of a pricing strategy over a period of 3 years. Current price is $100, and these are the factors up and down. So $100, if it goes up, it'll be a certain value. If it goes down, it'll be a certain value. There are probabilities associated with each eventuality. Right? So V up is 100 times U. V down is 100 times D. If D is just the opposite of U, then it's just a reciprocal, so I only have to calculate one thing. So what are the values? That 20% value, 1.2 was U, 0.9 was D, right? And, I think it was, yeah, okay. So that's it. So, and we could just fill in this table for as many years as we need to. What do these things equal? Probability, the U and the D, assuming they're all increments of 1 year. So let's take a look at that price model. Remember the price model you did right in the first week, where you looked at historical data on the price of something with respect to the t value, the time variable. And it was an exponential growth function that we assumed. We observed and then assumed that was the thing. So we did the logarithm of both sides and regressed the log of p on time. And remember, I've already defined volatility as the standard error of this, right? Standard error of this. And the R is the average rate of growth. Okay? So this really, if we want to look at estimate values, this is plus or minus the standard error, one standard error. So this encompasses 68% of all observations. That's the standard way of doing it. Okay? So an estimate of P up would be, if it went up by one standard error, then this price up value would be just the original equation times e to the SE, right? That's what this is. This comes from this. So U would be e to the SE, or the standard error. This standard error is the volatility, so the up factor is really just e to the volatility. Probability of up derives from simulating Brown. Oh my God, I don't even want to get into it. There's really great discussions online if you're really interested. We're going to use, and it comes from this kind of this formula, but bottom line, we're going to use this, where I forgot to change this. V is really the rate, the average rate, so that this is R. So this is the probability value of probability of going up. And so these are the three equations. U is the up factor, D is the down factor, and the probability is the probability of each of these in one year. So if I want to invest $100 in a stock and I've observed a 4% average growth rate and a volatility of 6.7%, P turns out to be 0.64. Okay. So the up factor is 1.1, the down factor is 0.9. So I could actually create this binomial lattice, filling it in like this. So what does this mean? It just means that this is the value at the end of year 1. This is the value at the end of year 2 if it goes up in the first year and down in the second year. And we can just fill these out like this. So if I followed, let's see, wait a minute now. Yeah, okay, we're going to do this again. One last time for 3 years. So we start at 0 and then grow or go down 3 years. So any given path, for any given path, I can find the total value of that path just by trailing through the tree. So let's say we have a fixed cost of 500, a production of 150 units per year, and a cost per unit of 30. I could find the present or the unit cost, of in this situation, if this happens. So it goes up in the first year and down in the second. The value, the cash flow in that year would be, here's the price I can charge, that's positive. The unit cost is negative 30. I'm producing 150 per year, and the fixed cost is 500. So this is the cash flow in the second year, if this happens. So I can calculate a set for a given tree. I can calculate a set of cash flows, and then apply the discount rate to them to get present values and all that stuff. And I'm going to show you that in our garage case example. So here's the cash flow tree, and I haven't discounted them to present value, but I could. The probabilities are these. I can, these are joint probabilities along the way. So joint probabilities, if you go for this one, for example, this one, right? I can get there from here or from there, and I have to add them up because they're two independent probabilities. This is an or, right? I can either get here this way or this way, so I add the probabilities. And then I can weight the values by probability, and we'll go on and on and on. We're not going to use this. I'm going to show you how we can avoid having to calculate probabilities. We can do these probabilities year by year by year if we want to, and sometimes in a given situation you might want to, but we will not need to do that for ours. Okay, that's it.